Okay. So yesterday, this is 3.1. This is the definition of a derivative. We talked a little bit about what a derivative was, and I gave you this definition. Limit as h approaches 0 of f of x plus h minus f of x over h. Definition 2 is limit as x approaches a. Sometimes they'll do this as a approaches b instead of x and a, of f of x minus f of a all over x minus a. And yesterday we talked about the derivative, we talked about a secant line here. And we can call this x and this a. Wait, no, let's reverse that. Let's call this a morning, this x. As x approaches a, those are getting closer to the tangent line, a single point. Or you can think of it this way as this is x. This distance here is h to your second point. So you got your 2 points. As h approaches 0, the points get infinitely close. We go from a secant line to a tangent line. So applying this definition, I'm going to get a little harder than yesterday's. Yesterday's did at a specific point, which makes it a little bit easier, but not a ton. In general, we're going to develop the formula that works for any point, and that formula is called the derivative. So my function is f of x equals x cubed. This one's a little bit of a pain in the butt. So we're going to do definition 1. Limit as h approaches 0 of x plus h cubed minus x cubed over h. Cubing your binomial is a little bit of a pain. I'm going to use the shortcut for squaring. First one squared plus both of them times 2 plus last one squared. If you have the binomial theorem memorized, you can just do that, but I don't think very many people do. Now I work it out, x cubed plus x squared h plus 2x squared h plus 2x h squared. So I did first times both of them and the second times both of them. 2x h squared plus, I'm on to third from the first, xh squared plus h cubed minus x cubed all over h. Wow. Such a nice, the x cubes can cancel. Now what's left after that? I have an h in every term that's left. Does that make sense?
Yeah.
And as I'm doing, now I'm going to combine like terms. X squared and 2x squared become 3x squared plus 2xh, nope, 3xh plus h squared. And that is a limit as h approaches 0. 0 goes in for h, leaving me with just 3x squared. Make sense?
Yeah.
Okay, now we're going to go to g of x. We'll use definition 2. Let's limit as x approaches a of square root of x minus square root of a over x minus a. Which, since x is approaching a, the denominator is 0, just like the h. So in order to make this limit work, this is a trick on limits, I rationalize the numerator. Yes, I'm moving my roots to the denominator. Welcome to calculus. Most of rationalizing the denominator's use in pre-calc is learning how to rationalize and move things around so that you can do this in calculus. Now these are conjugates giving me x minus a in the numerator. Okay, guys, can you keep it down a little bit? I'm making a video for Coleman. And notice something that cancels out. The x minus a's.
Yeah.
That is the beauty of this. Gone. Leaving me with 1 over square root of x plus square root of a. I can now plug in the a for x, leaving me 1 over square root of a plus square root of a, or 1 over 2 square root of a. If you're thinking about it as your derivative, derivatives can be notated in 2 different ways. If I'm writing it as f of x, I can call it f prime of x. F prime means derivative. The other way to write derivative is dy dx. And we'll go into the theory of what that means in a few weeks. But for now, it's simply notation that means derivative. And yes, I did change the a back to an x. Now we're going to talk about connecting a graph to its derivative. And this is probably easier to see if you look at page 97 in the book, but I'll sketch quickly the graphs here. So this is my function. We'll call it f of x. The graph, the y-coordinate of the derivative graph is given by the slope. The slope here is kind of steep, right? Goes to 0 at point A. So it starts steep, which means a high y-coordinate. The book shows it at 4. Goes to 0 at point A. We can see that the slope is negative here until B, where it is back to 0. The slope of the tangent line, anytime it is horizontal or a max or a min, that is 0. So if we get over on our graph here to B, Those are roughly this. They're supposed to be the same distance. We're negative there, and then we get positive again. The keys when you're sketching these graphs, which we'll be doing a lot more of in future weeks, is getting the zeros correct, positives for positive slope, negative derivatives where there's negative slope. Steeper means higher. Or steeper negative means further negative. Okay, that's graphing f prime from f. Now let's talk about going the other way. So I'm going to need to graph f of x given f prime of x. Everything is 1. And I'm going to label these slopes because it's a little hard to tell from my drawings. So we have a slope of -1 and a slope of 2. And this is the graph. Oh, nope. I did this wrong. That's supposed to be f of x. This is going to be easier than that. So this tells me that my slope of my original has to be 2. It changes here at 1. Now, what I'm not told is where this point is. You could pick, so it says sketch the graph such that f of 0 is 0. Okay. So that means I have to go through this point. I have a slope of -1 and it goes till x is 1. Then I have a slope of 2. Okay. It told me that the derivative was shown here and that it was continuous. If it wasn't continuous, I could have a jump here. Okay. There's a lot, the derivative produces multiple possibilities for a graph. I had to know a single point to know it was that. If they didn't tell me any of the points, it could be this. Okay, that would still have the same derivative. If they didn't tell me it was continuous, it could be, or a point, it could be that. And yeah, same slope. Okay, so it's important that they give you some hint, okay? Last thing we're going to talk about is a one-sided derivative. Actually, I don't know why I'm clearing this all out. I'll just move up. A one-sided derivative means it's a different derivative on different parts. Okay, so here is my graph. It's a nice piecewise function given by this. Okay, so if I look at the derivative at 0, limit as x approaches 0 from the left of 0 plus, so now I'm using this one. I use the upper function, the x squared. 0 plus h squared minus f of 0 is 0 over h, giving me h squared over h which gives me h, which when I plug it in is 0. That makes sense?
Yeah.
Now as I do it from the other side, I have to take the right-hand derivative. And I'm using the 2x. 2 times 0 is still 0. Which this limit equals 2. And we get a separate derivative. Okay. That is the definition of a derivative.